everyone. I was invited to talk about how we have been using Globus for a few applications in big data physics research. And I selected a topic that is very close to my heart, which is gravitational waves. And so gravitational waves made a big splash in 2016, but everything started in 2015. And I want to start with why this is important, so the physics of the problem and then the computer science aspects. And so the physics here is that we are able to observe, so to speak, objects that do not emit lights, like black hole collisions. And they reveal a lot of information about the universe that we cannot see with telescopes. And the beauty of this is that these devices, interferometers on Earth, are able to see this merger billions of light years away from Earth. So it is really remarkable. And these signals are very weak. That's a blessing and that is a curse. It is a blessing because all the information that these gravitational waves contain about black hole collisions is not lost as they travel throughout the universe. Now, it is an issue because since they interact very weakly with matter, they interact very weakly with interferometers. So that is the challenge to identify them. But over the last few years, these detectors have unveiled, so to speak, the curtain behind the gravitational wave spectrum. And as you can see here, there are a ton of objects that have masses that we had never even imagined with electromagnetic devices. All of them are here. And because of this, we had a bias, thinking that because we had observed a lot of neutron stars, when the LIGO detectors were capable of making any observation, they could see for the most part neutron stars. But that's not the case. The gravitational wave spectrum is remarkably different to what we had studied in the past. Okay, so what is the challenge? We have these devices, they can see very exciting celestial objects. How can we go and accelerate discovery? How can we leverage the resources that we have and try to understand the universe better? Well, we have theory, general relativity. We have numerical methods. This is to try to process data. And then data-driven methods. And there are big differences here. The methods that we used in the past were okay because we did not have a deluge of data and of detections. So in the past, when we were observing one event every 3 months, that was fine. I mean, we had dedicated supercomputer clusters to do that. But once you start getting into the regime of seeing several events per day, this is no longer scalable. So template matching on model searches are no longer scalable. And then we have these physical experiments. Now we have real data. We see how these signal processing algorithms work. And based on our own experience in the past, for example, using blue waters to go and reproduce the detection of the first neutron star collision, we realized that that approach was not scalable. We needed days of supercomputing to identify these sources. So what we proposed back in the day was to use neural nets to accelerate discovery. And it was very interesting, 2017, but those models were just prototypes. What we did in 2021 was to create an ensemble of models. And just for a comparison, back in the day, we only needed about 40,000 model signals to train one of these nets because we were only considering the masses of the sources to create model waveforms. But if you want to be, production scale realistic, you need to include a higher dimensional signal manifolds. The objects have masses and they rotate. And so that means that we now need to use tens of millions of model signals with multiple realizations of noise. So using one GPU for 3 hours as we did in 2017 is no longer a solution. So we used the Summit supercomputer and we were able to scale the training up to 1024 1024 nodes, that is over 6,000 GPUs, and then reduce the training to about only 3 hours. And so by doing that, we were able to train a set of models and then select the ones that perform the best. And then creating an ensemble allowed us to process data at the scale for the first time. And the beauty of this as well is that many scientists that have tried to search for gravitational waves in the past try to model the noise. I think that's too ambitious. a little bit arrogant. We cannot tell noise what it is. We can learn from noise and then try to tame it. And that is why we use neural nets. And so once we train these models, this is the other part of the community vision approach. You develop these tools. It takes a lot of time, a lot of expertise, combining supercomputing with AI. Well, we release the models. And so this resource, the Data and Learning Hub for Science, is critical for this type of work. You create the models, you release them, and then the community confirms what you're finding, and then they can further develop the models. And so after releasing the models, I was fortunate to know at the time Ben Blasik, Ryan Chard, Ian Foster. And so the next question was, okay, we have the models, can we actually go and reproduce your results? In the sense of, you are using this supercomputer to do the analysis, can a user that is not an expert on this type of work just grab the models and run the analysis on another supercomputer cluster? And the answer is yes. What you can do is you can connect DL Hub with your supercomputer cluster that you fancy the most, and then use PhunkX to do the computing. So PhunkX, you know, fires up the workers, and you do the inference on your supercomputer. And our colleagues at UChicago grabbed our models, and they did the analysis. Even though they don't know gravitational wave astrophysics, they know computer science. And so the outcome of that analysis is that we started using thousands of GPUs to accelerate the training. Now we use this cluster at NCSA that has only 64 GPUs to distribute the inference over the entire system. And so we found that by using that ensemble of 4 AI models, we could go through 1 month of advanced LIGO data in just 7 minutes. And the beauty is that you can see here that month of data. Green is when the 2 detectors are responsive, they are collecting data. And we have these 4 red lines, which is when we reported black hole mergers. You can see that we agree with the identification of these signals, and we made no mistakes, which is pretty good. And why is that? Well, because the first generation of models we had were making mistakes every 200 seconds, which is lousy, right? But you know, it was a prototype. It was a really good idea. But now we are making no mistakes in 1 month of data. That is remarkable. And all of this is reproducible, and the models are on DL Hub. And last time we checked on how many times they had been used by non-us, people about 1,000 times had used these models or invoked them to do analysis, which is great. This means that people are interested and they are using the models. Now, this is not enough, right? If we have done this and we have demonstrated that we can do this, so now we want to ask the question, can we do that at scale beyond 1 month of data? And so, well, before jumping there, this is the paper. It was published in Nature Astronomy. I was asked by Nature to write a blog about the human aspect of how this was done. So it is not about supercomputers or data infrastructure. They wanted to know the human aspects, like how researchers from different communities got together to address this problem. And then we also got this recognition from HPC Wire. Okay, but now going into how we do this at the scale. So the name of the game is, we now know how to use Summit. We developed some distributed training algorithms with NVIDIA and scientists there. And then we identified the sweet spot to train these models very fast and with optimal classification performance. We selected those using, for example, ROC curves or any other metrics for classification accuracy. And then we first tested the models at NCSA and then deployed them on the Theta GPU supercomputer at Argonne. Now, this computer has A100 GPUs. Each node has 8 GPUs, and they have about 160 GPUs in total. Now, this is not of the scale of Summit for training, but it is a very good sandbox for inference. And so in the past, we used the traditional models for inference, and then we optimally address IO and all of that. But now the question is, what happens if you take the traditional models and you turn them into optimized inference engines? And for that, we use NVIDIA TensorRT. And so these 4 models were converted into these TensorRT engines, and then we distributed inference over the entire machine. And this sounds a bit trivial, but when you go and start playing with TensorRT, you realize that off the box, it works well on one GPU. And then you need to learn how to distribute inference on multiple GPUs and then across the entire machine. So we got that right. And after doing this analysis, we realized that we were able to accelerate the processing of real data over 50,000 times faster than real time. And when we talked about this a few years ago, people were like very skeptical about, can you really process data faster than real time? Well, of course, and we can do it much faster than that. Now, the next step, as I mentioned before, is what happens when you process not just 1 month of data, but many years worth of data. And so at this point, advanced LIGO does not have 5 years worth of data. So what we did was to grab the experimental data sets and then do time slides, okay? You take, for example, Hanford data and Livingston data, and then you advance one with respect to the other by 1 second. And then if you're considering 1 month of data, well, now you have 2 months. And you continue doing this process until we obtain 5 years worth of data. And of course, we can blaze through these data sets. And what we found is that on average, these models make a mistake of about 1 for every month of data. And just for context, when you consider other pipelines that are doing, for example, template matching, when they find a signal, they give you a ranking of about 10 more triggers that look promising, okay? What we are saying here is that we are making a mistake just once every month. So this is computational efficiency, right? You don't need to go and search for the other 10 more plausible noise triggers. We are giving you the signals and some potential mistakes once every month. So that is quite remarkable. So let me tell you what is the vision of where we are going with this. And I'm pretty sure that this is something that many people across multiple domains are pursuing. But let me try to describe this for you. So you begin by training models in supercomputers. You use thousands of GPUs to reduce time to insights. Once you develop the models, you want to share your knowledge with your colleagues, because not everybody is going to access a supercomputer, or not everybody has the skills or the time to go and train how to do this. And they don't have to. If you have done that, then you go and share your knowledge. People go and get access to your models through DL Hub, and then they can connect DL Hub to their own resources with PhoneCakes. And if they are adventurous, they download the models, they can optimize them for inference at the edge, and then they can go and do AI-driven discovery, okay? But at some point in time, if you are, for example, considering a large-scale scientific facility or an imaging facility, you will realize that your models are not very good anymore after maybe 1 month of data that has been processed, or maybe after a few minutes. It depends on your application. But you don't want to go back to the supercomputer and wait for hours, if not days, in line or in queue to retrain your models. What you would like to do is to have access to cloud resources or any other online resources so that you can do a form of active transfer reinforcement learning. That way you fine-tune your models within a few seconds or minutes, and then you go back to continue doing science. Now, maybe after several months, the models are no longer giving good predictions. Well, in that case, you go back to the supercomputer and refine your models. And then you go back and start the cycle again. Why would you like to do this? Well, because you want to optimize computational resources, okay? And if there is no need to go to a supercomputer, well, don't do it. If you can stay in this cycle for longer, that is great. So this is what the vision that we have. And behind this, there are a lot of different factors that you need to take into account. For example, when you are broadcasting data into the models, make sure that you understand what you're broadcasting into them. And here is where you need to be concerned about fairness of your data, right? That you have sufficient metadata information to understand that the data is sane for analysis, okay? So that you put the blame where it should go, on the performance of the models or on the quality of the data. So it is a shared responsibility between experimentalists, computer scientists, and those that are interpreting the results of the models. So I think this is where I want to end Many disciplines at this point are realizing the need to try to leverage modern computing environments. So those that produce data, that collect data, need to talk, very closely with those that are harnessing these AI tools or advanced computing environments, because we want to maximize the use of this. And at the end of the day, if we really want to have AI guide discovery, we need to help AI get to that point. So this is about how we prepare the data sets, how we find the interplay between data and models, because they are not different, right? They are just expressions, different expressions of data, maybe in a structured manner. And this is at the end of the game. Once we have AI going in the right direction, we are going to learn from AI now about how we are going to configure these computing environments. What is the optimal way to use cloud resources, supercomputing, etc. And if we do this right, the main challenges will not be computational. They will not be scientific. It will be just human challenges, how we get to talk to each other. And if we are able to do that, then doing the last part, connecting resources, advancing AI, will not be that hard. It's just about getting humans to work together. And that's it. Thank you. Juan.
Thank you very much. Thank you, Elio. Great talk. Questions for Elio?
This is really interesting. You mentioned that you after a month of data or something like that, you have to fine tune the model. Why does it get bad over time? What is it about it that's causing that?
So there are many different reasons. One of them is talking about the LIGO detectors. They are affected by instrumental environmental noise. If you're gathering data when you have a dry season, it is very different to when you're collecting data when you have a rainy season, or when rattlesnakes are attacking the interferometers, right? And this is real. So over time, the statistics of the noise change, okay? So yeah, you can train models using, for example, February data, and maybe by May, you are not capturing the statistics of the noise. Mm-hmm.
So you mentioned that you get back not only here's data points, but here's a list of possible errors. Do you also get back confidence information? In other words, like, here's a list of possible errors, but this is the more likely error, this is the less likely error.
Yes, and so here is where you want to attack the problem not just from a computer science perspective. So in the models, we have a lot of domain knowledge incorporated into them. So I mentioned that we have 4 models. This is the ensemble. And so what you could do is you go and look at, for example, a noise trigger that looks very promising in the data stream. But then you go and look at it and you realize that in the Hanford instrument and in the Livingston instrument, the point at which you have the maximum energy of that or power of that event is dephased by about 0.5 seconds. And you know that the light travel time between the 2 interferometers is just 10 milliseconds at most. And so you say, hey, this cannot be correlated. This is not a real signal, because at most they should be dephased by about 10 milliseconds. So you discard that thing. The other is all these sources, depending on their mass, that determines when they are going to merge. So the frequency at which you will see a sharp increase in power in a frequency versus time spectrogram. If you see that one of those is merging at, for example, 140 hertz, and the other one at 50 hertz, you're not talking about the same event. And we have all these consistency checks in the model so that when you see an interesting trigger, you do a very fast post-processing analysis and you say, all of these guys meet these physics requirements, they look plausible. Mm-hmm.
Right, thank you. Let's thank our speaker again.